Hello guys, in this video I will be explaining about test of differentiability. So in order to test whether a function is differentiable or not, we should take its derivative. If there is a derivative is defined, then it is differentiable. If not, it's not differentiable. But for some kind of functions like this in this example, without x it's an oscillating behavior if you remember. X sine 1 over x, we studied this in Seque's theorem. And x squared sine 1 over x. So there are just these two questions in the book that we cannot take their derivative. There's no way to take their derivative unless using the limit. So for these kind of questions and for others also we can apply this. We are going to use limit form. This is the limit form that we studied in the previous lesson. It was the third limit form, which gives us the derivative of the function at c. So if this limit exists, we will know that there's derivative is defined. If that limit does not exist, and we will know that there's no derivative is undefined. So if it's undefined, then it's not differentiable. Okay, if there is derivative, it's differentiable. If not, it's not differentiable. So for the functions that we cannot take derivative, we are going to apply this form. If limit exists, it's differentiable. If not, it's not differentiable. So let's take a look at those two questions that's in the book. These are the only questions about use requires using this limit form. For the others, it's not necessary. We have other ways too. Okay, this question. Is this function differentiable at x equals 0? So it also means, does limit exist at, we know that f prime of x equals limit as x approaches to c, which is the number that we are using this as a critical value here, 0, of f of x minus f of c, which is 0, divided by x minus c, which is 0. So we are going to check whether we have this limit or not. So let's try to write this by using the given function. So it's limit as x approaches to 0 of f of x, we use the given function, minus f of 0, the value of the function is found by using equal condition, 0, x minus 0. So here we have limit as x approaches to 0 of x squared sine 1 over x over x. So there's simplification. X from denominator and one of the x from numerator will go. At the end, we'll have limit as x approaches to 0 of x sine 1 over x. So what's the value of this limit? We studied this in Seque's theorem. We have these kind of limits involving oscillating behavior. An x function multiplied by an oscillating behavior gives us 0. So limit exists, there is limit. F prime of c, our c here is 0. So f prime of 0 is equal to 0. So the derivative is defined. Derivative is defined. Limit exists. So we can say, since there is a derivative, this function is differentiable at x equals 0. All right. So this is the way for some complicated looking functions. Another question, same idea, same type. So let's write this in the limit form that we studied. Limit as x approaches to c, which is 0, of f of x, which is x sine 1 over x, minus f of 0, 0 over x minus 0. So ignore zeros. When you simplify x's, you'll have limit as x approaches to 0 of sine 1 over x. So there is no more x here multiplied by the oscillating behavior. It's alone. So remember what limit of oscillating behavior is. It does not exist. There is no limit. So this limit form means f, it's g prime of c, which is 0. So Since we don't have a limit here, we don't have a g prime of 0. So g prime of 0 is undefined since limit does not exist. So there is no derivative. We don't have any value for the derivative, so we say g of x is not differentiable. We can also use the same technique for absolute value questions if we need it, but generally we don't need it. This is not that practical because okay, let's move on. If the function is differentiable at a point, then it's continuous at the same point, but not the other way around. It's important. If a function is continuous, it may be differentiable, may not be differentiable. It depends on the situation. So, but whenever it's differentiable, whenever there's a derivative, then it is continuous, we are sure. Let's take a look at some graphs, some functions that are not continuous. If a function is not continuous at a point, then it's not differentiable at the same point. Okay? If not continuous, not differentiable. Not continuous, not differentiable. So let's take a look at the examples of not continuous situations. We studied this in chapter 2. If there is a hole, function is not defined, it's discontinuous at the point. If there is a jump, limit does not exist, then function is discontinuous at that point. If there is a break, limit does not exist, then we can say vertical asymptote, then function is discontinuous at that point. So these are the situations that function is discontinuous, having a hole, jump, or break. In other words, function being not defined, limit does not exist, and so on. So these are the situations where function is not continuous, so it's not differentiable at that point. So we have other conditions too. The function may be continuous at a point, but it may or may not be differentiable at the same point. So just because it's continuous doesn't mean that it's differentiable. So we have some situations. We have three kinds of situations that function is not differentiable even though it's continuous. So let's take a look at these situations. The first one, having a vertical tangent. These kind of graphs. Having a vertical tangent means we have a function such as x to the power of 1/3. So top is less than bottom, top and bottom both are odd functions. So x to the power of 1/3, x to the power of 3/5, x to the power of 5/7, and so on. These kind of functions have vertical tangent line at a point, then not differentiable. It's continuous, but not differentiable. We can also take derivative of this and see the derivative will be undefined at this point. Another situation that function is not differentiable is absolute value functions having a corner. We call this as corner. Its undefined derivative of the function is undefined when there is absolute value. We can check this by either using the technique, the method that we used here in the first two questions, or we can write this absolute value function as piecewise and check the continuity and differentiability conditions. Then we will see derivative is not defined at the given point. And finally, we have a cusp condition. Cusp means the function of cusp will be like the butterfly. It will be x to the power of like even number divided by an odd number. Top is less than bottom, top is even, bottom is odd, like 2/3, x to the power of 4/5, x to the power of 6/7, and so on. Top is even, bottom is odd, top is less than bottom. So those kind of functions have cusp. So these are the situations that function is not continuous even though the function is not differentiable even though they are continuous. Okay, having a vertical tangent, corner, and cusp. So we call these three as sharp turns. When we have sharp turns, then function is not differentiable. So these graphs are important. These ideas are important. So let's take a look at the ministry question. Which one of the given functions below is differentiable at x equals 0. Option A, there is a corner, absolute value, there is a sharp turn, no. 1 over x, there is a vertical asymptote. You can say vertical asymptote or break, or you can say not continuous at x equals 0. It's discontinuous, so it's not differentiable either. X to the power of 3 over 5. Is that one of the situations that we mentioned above? 3 is an odd number, 5 is an odd number, top is less than bottom, so this is vertical tangent situation. This graph is something like that. So even though it's continuous, it's not differentiable either. But this one, we haven't studied such thing. It's something like that. So it's not one of those situations that function is not differentiable. So having corner, having a break, or hole, or jump, or vertical tangent, or cusp means it's not differentiable. Otherwise, it's differentiable. Let's take a look at these exercise questions. Find the values of x where function f is differentiable. So there are infinitely many numbers that function is differentiable. So just find the numbers that function is not differentiable. So in the first question, there is a break at x equals -1. So it's differentiable at all real numbers except -1. We can say it's discontinuous at -1. There is a break at -1. Discontinuous, we can say break. So we should exclude this number from all real numbers. So this one, we have sharp turns here at -3 and 3. So we have corner, we can say sharp turn, we can say cusp. It looks like both. So the function is differentiable everywhere except those two sharp turns, negative, +3. Right, last one. I see a cusp here. Whenever you have even over odd power, top is less than bottom, that's cusp. So it's continuous everywhere except this cusp point, the sharp turn here too. Okay, from the graph, it's easy to identify from the function. So what makes the base 0 when the power is even over odd, top is less than bottom, will be the cusp point. For the corner, what makes absolute value 0 will be the corner point. For discontinuity, what makes denominator 0 will be point that we should exclude from all real numbers. Okay, next question, administrative question. Which of the following is true for this function? It has vertical asymptote at x equals -2. If you input -2, there is vertical asymptote. The result should be non-zero number divided by 0, right? It should be undefined condition. But here, when I insert -2 for x, I get 0 over 0. So no, it doesn't have a vertical asymptote at -2. So it's false. Plus, you remember the graph of this kind. It's 1 for greater than -2. And it's -1 for x less than -2. Okay. So there's no vertical asymptote. The function f is differentiable. There is no way the function to be differentiable because it's not continuous. What makes denominator 0? X equals -2 makes denominator 0. So it's not continuous at 2 at all. So it's false. Function is continuous. No, if it's not differentiable, not continuous. So it's clear that it's not continuous. -2 makes function undefined. And last option, the function is discontinuous with non-removable discontinuity. That's true. We know that there is discontinuity at -2, but is that non-removable or removable? It's non-removable since limit does not exist. Right side limit is different than